Yeah, it's not.
This meeting is being recorded.
Okay, so hello everyone to the second seminar in this seminar series. Today we have Justin Kaidi from Simon Center talking to us about Kramers-Wannier-like duality defects in 3+1D case theories. Go ahead, please.
Okay, great. So thanks so much for having me. It's a pleasure. So today I'll be telling you about this work that was done in collaboration with these two fantastic collaborators, Kantaro Omori and Yunshin Jung. And actually, before I get started, let me just give two small advertisements. So one is that my collaborator Yunshin has given a talk on the same subject at CMSA already. And so this is also on YouTube. And in my mind, that's really like the perfect version of this talk. So for those of you who do not like my talk, please feel free to check that talk out instead. And the second advertisement is that there were two papers that were roughly contemporaneous to ours, which are these two here. This one focuses more on a lattice perspective in T2 gauge theory. This one focuses mainly on continuum stuff, but gives complementary examples to the ones I'll discuss today. So if you're interested, please check all three of these papers out. Okay, so having said that, let's get right into it. So the basic topic of today's talk is going to be symmetry. And I think that it goes without saying that symmetries have been a guiding principle in theoretical physics for at least the last century. But really just within the last decade, we've had various new extensions of the notion of symmetry that have been shown to be very powerful and useful. So this includes, but is not limited to, higher form symmetries. These by now, I think, are fairly standard, fairly familiar to everybody. They're about 8 years old. There are vector and multipole symmetries, as well as subsystem symmetries. These are maybe slightly less familiar, but they've seen great utility in understanding things like exotic phases of matter, say fractons, etc. And there are also non-invertible symmetries, which will be the real main players of today's talk. These are symmetries which go beyond the paradigm of a group. And I'll give a much more detailed introduction to non-invertible symmetries in a moment. Also, at this point, let me already just pause and say that there's really going to be an egregious lack of references in this talk. So if I've forgotten to cite your work appropriately, then I'm sorry about that. Hopefully I've cited appropriately in the paper. If not, let me know. Okay, so before giving any details on this, I just want to step back and say that all of these different advances in the notion of symmetry have stemmed from one big conceptual breakthrough, which is that symmetries should be thought of as synonymous with topological defects. And we're going to see a lot about this correspondence in a moment, but for now, let me just give you sort of the basic intuition for why you should think of symmetries as synonymous with topological defects. The basic reason is that the set of topological defects will prove to be a robust and persistent feature of the theory at any energy, meaning that if you have some set of topological defects in the UV, you expect to have that same set in the IR, and you can use this to constrain the dynamics. So this is a lot like how we use symmetries, and since their sort of uses are very similar, it's useful to just conflate the two. Okay, so let's give a little bit more detail on this correspondence here. And to give more detail, it's actually best to start in 2 dimensions where the rules of the game are very clear. So let's start by reviewing some of the salient features of 2 dimensions. Okay. So in general, you can have topological defects of various codimension. And in 2D, there's just codimension 1 and codimension 2, which makes things simple. So the codimension 1 defects are, of course, lines. And we can also, in general, have codimension 2 topological defects, where these are local operators. And topological, in this case, means that it doesn't matter where I put these local operators. Okay, so I'm going to allow for codimension 2 topological defects, which can act as junctions between 2 lines. Okay, and so in particular, I can have this codimension 2 defect O between LA and LB here. And one particular case of this is when one of the lines, let's say LB, is the trivial or identity line, in which case this O acts as an endpoint. Okay. Now, a useful way to sort of phrase this, a useful language to talk about this, is to think about the lines as objects and the local operators as some maps between the objects, or morphisms. And this data of objects plus morphisms gives rise to the structure of a category. Now, in the current case, we're going to want some notion of fusion. We're going to want to be able to fuse two lines. As we'll see in a second, this is sort of like the composition law of a group, if there's some group. More generally, it's the composition of two symmetry actions. And so this will give rise to some extra structure which promotes this to a fusion category. We'll talk more about fusion in a second. And also sometimes you'll want unitarity. So then you actually have to talk about unitary fusion categories. But for today's purposes, let's just forget about unitary. Okay, so in 2D, the set of symmetries, that is to say the set of topological defects, form a fusion category. And so what's this fusion that we've been talking about? Well, some of the defects might have so-called a group-like fusion. What this means is that I can take one of the defects and fuse it with the second defect, and I'll get out a unique third defect. Okay, so if I call this LG1 and LG2, then I'll call this one LG1G2. And if this set of defects closes on themselves and are inverses, then this will really give some representation of a group. And I should think of these defects as generating some group. But sometimes you'll have not group-like fusion. You'll have something more general like this. So I can fuse two defects, and then I'll get not just one defect out, but a sum of stuff. And since I have a product and a sum here, this doesn't have the structure of a group, but rather that of a ring. So in general here, the fusion is a ring. So in order to specify the category, I should specify the full fusion ring, set of all fusion rules. But actually the category knows about more than just that data. And in order to explain this, it's useful to just focus on the group-like part for a second. So we know that associated to any global symmetry group, I can have some 't Hooft anomaly. And the category turns out to know about those 't Hooft anomalies. In this language that we're using right now, that is captured by a crossing diagram like this. Okay, so this might not look like it, but this is just the usual crossing diagram that you're familiar with. I can go ahead and rewrite it in more standard form, something like this. And over here you have LH. Okay, so this is just a usual crossing equation. And the point is that sometimes when you do this crossing move, you can produce some phase alpha here. And this captures the 't Hooft anomaly of the group. And this is part of the data of the category. Now, what about for this sort of fancier non-group-like fusion rules? And also, let me just say briefly that when we have these non-group-like fusion rules, we say that the corresponding defects generate a non-invertible symmetry. The reason that it's called non-invertible is the following. Well, in this group-like case, it's clear that I could take G2 to be equal to G1 inverse, in which case what I get here is just L of the identity. So I'd get the trivial defect. And so that would mean that this line has an inverse. Whereas in this case, that's not true anymore. I could take G2 equal to G1 inverse, and then maybe this line becomes the identity, but this line will not. So this is said to be a non-invertible symmetry. Okay, so in the case of a non-invertible symmetry, there's no 't Hooft anomaly proper, but there is a generalization of the 't Hooft anomaly, which can be captured by just looking at the same sort of diagram here.
Sorry, could I ask a quick question? Could you
Yes,
could you say a few more words about why this non-associativity is capturing a Tufte anomaly, perhaps in terms of background fields or?
Sure. So let's consider just discrete symmetries, which is generically the case that we're considering. Then the background gauge field is a flat connection, and specifying the background gauge field is basically like specifying some bundle structure over space. Now, the usual way one specifies a bundle is to split your manifold up into some open patches, like so. Let's call this UI, UJ, UK. And between any two patches, you're specifying some transition functions. Let's call them G, I, J, and so on and so forth. And on each of the triple intersections, UI, UJ, UK, you're specifying some cocycle condition, like so. Now, the point is that you can basically replace this picture that I've drawn here with a picture like this, where you're just labeling each of the lines by the corresponding transition function, Gij, so on and so forth. And so the picture you get out is exactly the sort of trivalent network that I've drawn here. So you can think of each of these networks as specifying a background gauge field. And this sort of crossing move is just sort of changing the triangulation, if you will, or the way you split this thing up into open patches. That just corresponds to some gauge transformation. So this is saying that when you change the background gauge field by some gauge transformation, you might produce a phase, which is just the usual notion of Tufte anomaly.
That's great. Thank you.
Yeah, thank you. Okay, any other questions? Okay, great. So let's go ahead and talk about the sort of generalization of a Tufte anomaly to the non-invertible symmetry, very briefly. And as I was saying, this is really just captured by the same sort of crossing diagram. The only real difference in the current case is that now I have this sum here, where the sum is over these internal channels. And the reason I have this sum is because now LH and LK do not have a unique fusion channel by nature of being non-invertible. So they have a bunch of stuff, and I have to sum over them with some coefficients. And these coefficients, which are called F symbols, are sort of like the generalizations of Tufte anomalies. So the upshot is that in 2D, symmetry is captured by a fusion category. And to specify the fusion category, I have to specify the fusion ring as well as the F symbols, sort of generalized Tufte anomalies. Now, I can't just specify any data. There's some consistency conditions that one has to satisfy. In particular, there's this so-called pentagon identity. I'm flashing it here, but it really won't. Yes. Was there a question?
A small question from Usa. Are these F also phases? Hi.
Sorry?
Are these F also phases?
Phases.
Yes, like the alphas, the Tufte anomalies are phases.
That's right. Let me think. I think...
Or do they satisfy some property? I mean, like...
I think they don't have to be phases.
Uh-huh.
Yeah, I think they do not have to be.
They're
in general
more interesting constraints.
Sorry.
So they satisfy other types of constraints, though. Like this pentagon identity is an example of a constraint that they have to satisfy.
Yeah, that's right. So, for example, I do not think that these things will be valued in group cohomology like the alphas were. Though, maybe I should defer that question to Laksha, who probably knows much better than I do.
As far as I know, they have to satisfy this pentagon identity.
Right.
And then they don't need to be phases.
Okay, great. So, indeed. Okay. Yeah, thank you.
Can I ask a follow-up then?
Yeah, please.
If you are in the standard case for a group-like symmetry, then does the pentagon identity imply that this is a phase?
Yeah, so I think the pentagon identity in that case will be roughly like the cocycle condition for that alpha. So that's just going to imply that it's a cocycle, And so this basically implies, so there's two, so alpha takes values in group cohomology in general. So H is 3. And the co-cycle condition comes from this pentagon identity, and the sort of mod exact stuff comes from a certain ambiguity that one has in assigning phases to these triple intersection points. So this pentagon identity for alpha is just the co-cycle condition.
Thank you.
Yeah. Great. Any other questions?
Just a comment. So when you have this non-invertible case, right? So like you're going from LH, LK to LY, then so it can be like a projection, right? If you have a LH, LK can go to LY plus LX, then you can involve going to one of the LYs can be like projecting in this from a two-dimensional space to one-dimensional space. So it can involve something like 1 over square root 2. And so it doesn't have to be a phase.
Right. So you're giving a concrete example where it's not a phase. Right. Right.
Yeah.
Yeah. Great. Thank you. Yeah. Okay. Great. So so the data of the category was the fusion ring and the F symbols. The F symbols were subject to some identity here, the details of which are not important for us today. And it turns out that this is the full sets of constraints on this data. So this is really the only constraint. But nevertheless, already, it turns out that this constraint is strong enough to restrict you to a discrete set of solutions. This is something which is known as Ochnino rigidity in math. And this is part of the reason why we say that these things should be RG flow invariants. There's not really continuous deformation classes of these symmetries, and so we expect them to at least not change continuously along the flow. Okay.
Sorry, question, just to clarify. So this means that if you fix a fusion ring, is that right? That then there is a discrete set of solutions to this?
Yes.
That's okay.
So you choose some fusion ring, and then you assign some associators like this, and then you try to solve for those using
okay.
this. There's a discrete set of solutions.
Right.
Yeah. Okay. Great. So thanks. Okay, so actually for today's talk, we're not going to discuss these F symbols at all. And so the reason why I mentioned them was basically to tell you that, so throughout this talk, I'm going to maybe colloquially use the word category, but I'm never really going to talk about the full categorical structure, whatever that might be in higher dimensions. We'll eventually talk about higher dimensions. So today I'm really only going to talk about fusion rings. Okay, so that's just a sort of caveat. Okay, so in the back of your mind, just remember that there's some data that I'm not really telling you about. All right, but so let's focus on fusion rings for the moment. And let me tell you about one particularly interesting fusion ring, which will be a central player in today's talk. That fusion ring is the following rank 3 fusion ring. Rank 3 just means there's 3 lines which participated. There's the identity line, there's this line eta, which has a Z2 group-like fusion, and there's this N here, which has non-invertible fusion because it squares to a sum of stuff. Now this simple fusion ring is very nice because it's realized in one of our favorite sort of concrete physical systems, which is the 2D critical Ising model. So in that context, the eta defect here, which is some Z2 defect, implements the Z2 spin flip symmetry of the Ising model. So if I think about realizing the Ising model as just some lattice model with spins at each site, then the Hamiltonian only depends on the relative spin differences. And so if I flip every spin, then that doesn't really do anything. So there's a Z2 symmetry, and eta is like the generator of that Z2 symmetry. Now what about this N here? The N is a non-invertible defect, and its interpretation is a little bit more subtle. it turns out to be closely related to a so-called Kramers-Wannier duality of the Ising model, or self-duality of the critical Ising model. And the way that one understands this is as follows. So roughly speaking, let's start with the Ising model. Let's call it T here. I can go ahead and consider an interface between the Ising model and the Z2 gauged version of the Ising model. So in other words, I gauge the Z2 zero form symmetry in half of the space. And let's put Dirichlet boundary conditions on this boundary here so that this is some topological defect. So this is roughly speaking like saying that I have the Ising model at temperature beta here and the Ising model at temperature 1 over beta here. Now, this interface between these two models is just that. It's an interface. It's not a defect in a single in general. But if I fix myself at the critical point where beta is equal to 1 over beta, so I'm in the critical Ising model, then the theory over here is the same as the theory over here. And it turns out that this sort of duality interface becomes a duality defect, self-duality defect. And this is this N that we've been discussing here. Okay. So this N is what we're really going to want to understand throughout today's talk. Okay, so we've seen that this N is closely related to self-duality. Okay. And it turns out that whenever you have an N satisfying these controls, is there a question? No. Okay. It turns out that whenever you have an N satisfying these fusion rules, then you'll have some notion of self-duality. And why is that the case? So let's see why that's the case. In order to do so, it's actually useful to generalize slightly, just to see the power of all of this. So it turns out that the Ising category is a special example of a larger class of categories which are known as Tombari-Yamagami categories. So these have some sort of long, scary Japanese name, but they're actually extremely simple categories. They're really the simplest categories beyond just a group.
Excuse me, may I ask a question?
Yes.
How do you see that n squared is 1 plus eta? Is there a simple argument?
Sure. You mean from this picture here, for example?
Yeah.
Okay, that's a good question. So you're probably familiar with the fact, and if you're not, then we'll see it in the next couple of slides, that in order to gauge a Z2 zero form symmetry, what I should do is I should take all of the 1 cycles in this case. So let's say I'm on the torus or something. I look at all of the 1 cycles and I insert a sort of defects and I sum over all of the elements of Z2. So say this is labeled by G and H, and then I sum over G and H in Z2, right? This would implement the gauging. So in other words, to actually do this Z2 gauging, I have to insert a fine mesh of 1 plus eta, okay, on all of the 1 cycles, which maybe I should be doing this in a different color. So this is supposed to represent some fine mesh of 1 plus eta lines, okay, on all of the 1 cycles. Okay, maybe I went overboard, but that's what it's supposed to look like. And so if I put 2 of these ends, then roughly speaking, I'll have this 1 plus eta defect fine mesh of it in between the 2. So each of these is 1 plus eta. And now if I shrink this picture down and I sort of, bring the 2 ends really close together so that they're about to annihilate, I just end up with, say, 1 of these 1 plus eta lines left over. So this is sort of schematically how it works.
Thank you.
Yeah, thank you. Okay, great. So, good. So anyways, this Ising category is a special case of the Tombari-Yamagami category. Tombari-Yamagami of G contains elements which are just group-like elements, LG, and then 1 non-invertible defect, N, such that the fusion is as follows. The LGs just have normal group-like fusion, and the N squares to a sum of all of the group-like guys. Okay, so it's almost just like a group, and then there's just 1 extra defect, N. So if I compare this to the Ising case here, it's obvious that Ising is Tambara-Yamagami of Z2, right? So it's just one special case of this more general fusion rules. And it turns out that whenever you have a Tambara-Yamagami extension of a group G, then the theory is self-dual under gauging G. Pictorially, this can be argued for as follows. So let's just look at the level of the torus partition function. So this is supposed to pictorially represent the torus partition function. It's just this box here. And what I'm going to do is I'm going to nucleate a bubble of the N defect inside. So as long as I nucleate it on some contractible cycle, like here, then I can, of course, just shrink it out and get rid of it up to some factor that I'll divide by. So this is just some trivial identity. And now I'll take this N and I'll just deform it. So it's still on a contractible cycle, but now it just looks different. I've wrapped all the generators of H1. And now what I can do is I can note that here I have an N here and a second N here. So I can actually fuse these two together and use this fusion rule to replace that with this sum here over LG, which is this green line. And I can do the same thing on all four sides. And then I can shrink this circle in the middle down and get rid of this factor, and I'll get this picture. Okay, so here I've pulled out the sums out front. So this picture here is, of course, just the gauged torus partition function. And so the point is that if I have an N defect like this, then the theory before and after gauging is the same. And let me just emphasize that the reason why this worked is because N had the property that it squares to the condensate. The condensate is the thing that I have to insert a fine mesh of. I have to insert it, in this case, on all of the one cycles to implement the gauge. And if I insert this on the one cycles, I implement the gauge. Okay. So thus far, hopefully I've told you, or hopefully I've reviewed for you the fact that in 2D, the most general notion of a symmetry is captured by a fusion category. An interesting example of a fusion category, or really fusion ring, is the Ising fusion ring, which has this Kramers-Wannier defect N, which tells you about self-duality. And now we can get into the real bulk of today's talk, which is to extend everything that I said until now to higher dimensions. Okay. In particular, we'll mainly focus on 4 dimensions today. Okay, so the questions that we're going to ask today are, is there an analog of the Kramers-Wannier defect N in higher dimensions? And also, is there an analog of the Kramers-Wannier self-duality in higher dimensions? That is to say, does this N tell us something about the theory being self-dual? And I hope to convince you today that the answer to both of these is yes. All right. And so what is going to be the general philosophy, the way that we're going to approach this question? Well, our starting point will be to consider a theory with a certain mixed Tuft anomaly. Okay, so let's say I have symmetries G and H, and they have an anomaly. I'll then gauge part of the symmetry, let's say H, and I'll show that if the Tuft anomaly was chosen correctly, then G will become a non-invertible symmetry of Kramers-Wannier type. Okay, so that's what I'd like to tell you about today. So before getting into the 4D story proper, are there any questions about the motivation or the 2D stuff? Okay. If not, let's talk about the 4D results. So first, the setup. I'm going to consider a 4D theory on a 4-manifold X4. Now, technically, I'll take X4 to be spin. That will be important for some reasons, but I probably won't discuss it again. So if you're curious, please ask at some point. So I have a 4D theory on some manifold X4, and I have a Z2-0 form symmetry and a Z2-1 form symmetry. Now, by the sort of general philosophy that we've been exploring thus far, we know that a P-form symmetry has some corresponding defect, which is codimension P+1. And so in particular, this zero form symmetry has a corresponding codimension 1 defect D. It's codimension 1, so it will live on some 3 manifold, M3 in X4. And this D should generate the Z2, so D squares to 1. Now, the Z2 one-form symmetry will also have a corresponding defect, which is now codimension 2. I'll call it L, and L will also square to 1. Again, generate to Z2. All right. Now, let's say that these two symmetries have a mixed Hooft anomaly of the following form. So what is this? So this is the anomaly inflow action. So it's defined in 5D with the original 4D theory on the boundary. And A1 here is the background gauge field for the Z2 zero form symmetry. And D2 is the background gauge field for the Z2 one form symmetry. And well, for those of you who are sort of aware of this, technically I should replace this B2 cup B2 with 1/2 the Pointrosian square of B2. But this is again a technicality which is not going to be super important for today. So let's just think of it as B2 cup B2. Okay, so what really is important here is the fact that this anomaly is linear in A1, but not linear, in this case quadratic in B2. So that will end up being important. Okay, so I have these two symmetries, and I have this mixed Hooft anomaly. Now let's go ahead and, start with a warm-up. Let's go ahead and gauge the zero form symmetry. Okay, so I will go ahead and I gauge zero form symmetry, which means that I promote this background gauge field A1 to a dynamical little a1. And that means that so I take the original partition function, say, I make this big A a little a, and then I integrate over little a, and I get this new partition function, which is again coupled to the background gauge field for the one form symmetry. Then there's this other background gauge field for the dual two-form symmetry. So let me remind you that if I have a p-form symmetry in d dimensions, and I gauge it, then I'll, in general, get a d minus p form, d minus p minus 2 form, dual, also sometimes called quantum, symmetry. And this symmetry is such that if I gauge that, then I'll go back to the original theory. Okay. So we'll see a little bit more about this correspondence in a moment. But suffice it to say that if I gauge a zero form symmetry in 4D, then I end up with a dual two form symmetry. And the background gauge field for that is the 3 form here, A hat. Okay, so I'm gauging the zero form symmetry. And now I'm going to ask the following question. When I gauge this symmetry, what happens to the one form symmetry? Well, naively, there are two options. The first option, which we're probably most familiar with, is that I can get a 4D theory with the Z2 one form symmetry being broken. Okay, I get a sort of ABJ type anomaly which kills the Z2 one form symmetry. That's probably the most standard interpretation. But we're also probably pretty familiar with the second interpretation, which is that I can think of the theory as a coupled 4D, 5D system, where the 5D is sort of this inflow theory that we had. And if I couple the system to this 5D bulk, then I can actually preserve the Z2 one form symmetry. Okay, so these are the two standard options. And let me just rephrase these two standard options in the language of defects. So the two options are that I can have a 4D theory without any codimension 2 topological defect L, which would generate a one-form symmetry. Or I could have a coupled 4D 5D system with such a codimension 2 topological defect. These are the two standard options. But it turns out that there's actually a third option. And the third option is the following. So in this case, we had a 4D theory, but no defect L. In this case, we had a defect L, but we had a coupled 4D 5D system. It seems like we can't have our cake and eat it too. That is to say, we can't just have a 4D theory also with the defect L. But it turns out that you can have this. And that's the third option. So the third option is that you can have a 4D theory, and it also has the codimension 2 defect L. So it's really the best of both worlds. But the catch is that now this codimension 2 defect L does not just generate a one-form symmetry. Instead, it's part of some larger structure known as a 3 group, which is an extension of the one-form symmetry by the dual 2-form symmetry. This seems sort of technical, but it's really not. It's actually very easy to see how this option works out. So let's go ahead and see it. So let's begin by forgetting this piece here. So forget about that for a second. Let's just say that I have no anomaly, and I go ahead and I gauge the 0-form symmetry. Okay, so this is the original partition function. I'm gauging the 0-form symmetry, so I make big A into little a, and I integrate over little a. And I can, in general, have a coupling to the dual background gauge field for the 2-form symmetry, which is this piece here. And this will give me the gauged theory. Okay, so this is if there's no anomaly. Now, if there is an anomaly, then there's various things that I can do to make this thing gauge invariant under transformations of B2. Well, one thing I can do is I can just completely sacrifice this one-form symmetry and just throw this thing out. I can set this equal to 0 effectively. So that's basically option 1. Now, another option where I can keep the B2 non-zero, so I can keep the one-form symmetry, in other words, is to couple this thing to a 5D bulk, which is this term here. And so this is just the inflow action, and so clearly this thing is gauge invariant under transformations of B2. This is the second option here. And so what about the third option? So to have the third option, I need to cancel this M5 dependence while also keeping B2 non-zero. And we see that this is actually possible because of this piece here. In particular, this final term here can be rewritten using Stokes' theorem, as well as the fact that A1 is closed. So I can rewrite it as this. And now this term is linear in A1. The anomaly is also linear in A1. So clearly I can cancel the M5 dependence by choosing delta A hat, such that it's minus B2 squared. So we can get rid of the 5D dependence by demanding that A hat is not a cocycle, but rather something which satisfies this. And this is the sort of mixing that gives rise to the 3 group. Okay? So let me summarize that. So to summarize the discussion so far, we saw that I start with the theory with a Z2-0 and a Z2-1 form symmetry with this anomaly. And then when I gauge the Z2-0 form symmetry, there's 3 possibilities for what happens to the Z2-1 form symmetry. One is that I get a 4D theory, which has no codimension 2 defect, and hence no one-form symmetry. I can get a coupled 4D, 5D system, which has a codimension 2 defect, which generates a one-form symmetry. And finally, I can sort of have the best of both worlds. I can have a 4D theory, which also has a codimension 2 defect, but now the codimension 2 defect is part of a 3 group. Okay? And I should say, yes?
I would say the first and the third options are the same theory, because to go to the first option from the third option, I just turn off the one-form symmetry background.
Yeah, exactly. So, yeah, exactly. So if you take the third and then you just set the background equal to 0, you can interpret it in this way. Yeah, so indeed, that's true. It's sort of just an interpretational difference, I would say. But yeah, indeed. Thanks. Okay, so let me say one more thing on this slide and then ask if there are questions so far. So let me just say that thus far, everything I've discussed has been invertible. Okay, so I haven't actually told you about non-invertible defects. You know, I told you about this 3 group, which is sort of a fancy thing, but it's still group-like. And so next I'm going to want to tell you about how you can get non-invertible defects by basically the exact same reasoning. So before I do that, are there any questions on this part?
In the second option, excuse me, the
Yeah.
5D bulk, the Z2 zero symmetry is also gauged in the 5D bulk.
Is the Z2 zero form symmetry gauged in the bulk? Yes.
Yes, thanks.
Thanks.
I'm just curious, why is the focus on Z2 so much?
Sorry, what did you, could you ask again?
You could have some zero form symmetries which are not Z2 with a mixed anomaly. Does this?
Okay. Yes. So you could have not Z2, but things will become significantly more complicated in the ZN case.
Okay,
not
thank you.
particularly complicated, but there are complications.
Thank you.
Yeah, and I'll try and mention them when we actually get to the non-invertible case. So yeah, in the non-invertible case, there will be some complications. Okay, great. All right. So now I want to tell you how to use. Yes.
In the second option, the 5D bulk is not anomaly theory. Is it like is it invertible?
The 5D bulk. So the 5D bulk is basically this. So it was the anomaly inflow action, which was invertible, but then I've gauged the A1. I mean, this is the coupling that I am discussing.
Right. But is it one form gauge theory in 5D?
Is it a one form gauge theory in 5D? I think so, yes.
Right.
Sorry, one form gauge theory in 5D? No. Zero form gauge theory.
With one form gauge field, I think that one is the same question I asked.
Yeah. It's the same question, I think. I just try to confirm.
I think he asked the second option is the bulk is non-invertible, has a one form Z2 gauge field by gauging the zero form Z2 symmetry.
Yeah, this is what I have in mind here. Does that make sense?
Yeah.
Okay, great. Okay, so great, thanks so much. So any other questions? Okay, good. So now let's talk about the non-invertible case. So to do this, so thus far we gauged the zero form symmetry and asked what happened to the one form symmetry. Now let's instead gauge the one form symmetry and ask what happens to the zero form symmetry. All right. So again, there are two obvious options. One is that I can start with the one form symmetry and gauge it, and then I can either get a 4D theory with a broken Z2 zero form symmetry, or I can get a coupled 4D 5D system with an unbroken zero form symmetry. Said in a different way, I can get a 4D theory without a codimension 1 topological defect D, which would generate a zero form symmetry. Or I can get a coupled 4D 5D system with a codimension 1 topological defect D. And now let's ask about that third option. So can I use a higher group sort of structure to get a 4D theory with the codimension 1 topological defect? And the answer is no, you can no longer do this. It's actually fairly simple to see why you can't do this just at this level here. So let's return to this. So in the current case, the analog of this piece here, so I'm now gauging the one form symmetry. And so I'll get a dual one form symmetry. So I'll have a term like this. So this thing is linear in B, but this anomaly which will now look like capital A and then little b squared, is quadratic in little b. So I can't just, absorb this dependence here by changing the cocycle condition for b hat 2. Okay, and so I can't seemingly use the same tricks as before. So it seemed like I only have these two options. But the main point is that there is again a third option. It's just not a higher group anymore, it's something else. And so the basic idea of this third option, which we're going to give more detail on, is that what you can do is you can couple D, this defect, to some 3D TQFT I, such that I cancels the anomaly of D. And so N, which I'll define to be D times I, will be a gauge invariant operator. So it will survive the gauging. And so I'll get a 4D theory with this defect N. And as I'll argue right now, this N is non-invertible and it's of Kramers-Wannier type. Okay. So let's give more detail on this. So this TQFT I, what is it? Well, obviously the TQFT I is not unique. Okay. There can be many theories which match the same anomaly. But it turns out that there's a minimal option in some appropriate sense. And in the current case, the minimal option is U1 level 2 Chern-Simons theory. So the claim is that D is not a gauge invariant operator, but this combination here, which is D and then U1 level 2 Chern-Simons, is a gauge invariant operator. That's this N. And I claim that N is non-invertible and of Kramers-Wannier type. So how do I check that N is non-invertible and of Kramers-Wannier type? Well, I've given you the explicit form of N, and so all I need to do is check the fusion rules. And how do I get the fusion rules? Well, I just, do it explicitly because I have this explicit form. So basically you just multiply N with N. You use the fact that D squares to 1. And then you use some just really undergraduate level, change of variables, which I won't go through right now, but if you're interested, please feel free to ask me after. And, just a little bit of massaging of these integrals will give you this as the final expression. Okay, and so let me just tell you what this thing is in the final expression. So here I have a sum over surfaces sigma 2, which are in H2 of M3. And what's the summand? Well, I have this -1 to the q here. This is the triple intersection of sigma 2. Don't worry about this piece. It's not really that important. And then I have this L hat sigma 2, which are the generators of the dual one-form symmetry that I got after gauging the original one-form symmetry. Okay. So what can we see from these fusion rules? Well, the first thing we see is that since there's a sum here, this N is non-invertible. So that's the first thing. The second thing is that I can compute the fusion rules of N with this L hat and this L hat with itself. And they're very, very similar to the fusion rules we had for the Kramers-Wannier defect, which looked like this. And eta equals eta, and eta squares to 1. Okay. So this is really like the higher dimensional analog of these Kramers-Wannier fusion rules. Of course, there are some differences here. So a couple of the differences are the following. So first of all, we have this phase -1 to the q, which didn't have any analog in 2D. It turns out that this is actually not really an important difference because I can basically absorb this -1 to the q in a redefinition of L hat. So this is really not an important difference. What's a much bigger conceptual difference is the following. Whereas in the usual Kramers-Wannier case that we had here, where N is, it's a line and it squares to a sum over lines, everything here is a line. Here, in higher dimensions, we see that we're taking two codimension 1 surfaces and we're fusing them, and we're getting a sum of codimension 2 surfaces. Okay? So we see that we sort of mix things of various codimension. Right? So this is sort of a bigger conceptual difference. But it turns out that the real main utility of these Kramers-Wannier defects in 2Ds also carries over to 4D. And that is namely that these 4D defects, again, tell you something about self-duality. So there's a sort of formal argument for why this is, but instead of giving you the formal argument, let me just sort of give you the picture, which is a lot like the 2D picture. So remember in 2D, the sort of picture for how this worked is that you considered, let's say, the torus partition function, you nucleated a bubble of n, you deformed n so that it wrapped all of the generators of H1, then you pinched off, and you got an insertion of the condensate on all of the 1 cycles. So in higher dimensions, you can basically run the same exact argument, and that's what this is supposed to schematically represent. So this here is the insertion of n on all of the generators of H3. So it's really the analog of this picture. And then you go ahead and you pinch off using the fusion rules, and you shrink all the bubbles, and you'll get an insertion of a fine mesh of the condensate, which is supposed to be the analog of this. Okay? So let me summarize what I've said so far before giving some examples. So here's the summary. I started with a 4D theory with a Z2 zero form symmetry and a Z2 1 form symmetry with this mixed anomaly. I then first gauged the Z2 zero form symmetry, and I saw that there were sort of 3 interpretations for how you can think of the results regarding this 1 form symmetry here. You could either have a 4D theory without a codimension 2 defect, and hence no 1 form symmetry. You could have a coupled 4D 5D system, which has a codimension 2 defect, which generates a 1 form symmetry. Or you could have a 4D system with a codimension 2 defect, and now the codimension 2 defect generates a 3, or is part of a 3 group. Now instead, if I gauge the 1 form symmetry, and I ask what happens to the Z2 zero form symmetry, well, there are again 3 interpretations. One is that I can get a 4D theory without a codimension 1 defect, and hence no zero form symmetry. I can get a coupled 4D 5D system which has a codimension 1 defect, which generates a zero form symmetry. And finally, I could get a 4D theory which has a codimension 1 defect, but the catch is that now this codimension 1 defect is non-invertible. Okay, it's a Kramers-Wannier-like defect. Okay, so this is the main point. I'm now going to give you some examples, but are there any questions on the general idea?
Can I ask you about this minimality of this U1 level 2 that you used to soak up this anomaly? So
right.
If you didn't choose this specific theory, but something that had the same anomaly but wasn't minimal,
right.
How would it change diffusion? Would it change it at all?
Yeah, it would change, but the important thing is that...
couples.
Exactly. Yeah, so the non-minimality sort of comes in the form of, let's say how to say it. So basically what these authors here argued is that the non-minimality is as follows. So any theory which has, let's say, a Zn symmetry and k units of the anomaly for that Zn symmetry, any TQFT matching that anomaly is of the following form. It's some sort of minimal theory, which they call ANK, which really depends on the background gauge field for this Zn symmetry. And then something which is effectively decoupled in the sense that it doesn't depend on this B at all, this gauge field here. So yeah, so what you'll get is something which doesn't really affect this general structure of the sum over these dual 1 form defects, and it'll just be decoupled basically. And so really when we write these equalities, like n squared is equal to something, you should always take these equalities at the level of up to some completely decoupled TQFT. This is, for example, very important when you're trying to extend this beyond the Z2 case. You have to really just interpret this equality as up to decoupled TQFT.
Yeah, thanks.
Yeah, thank you.
This U1 level 2 Kramers also has a framing anomaly. Is it going to be important to you?
The framing anomaly, no, is not going to be important. I guess you can get rid of the framing anomaly presumably by stacking with some decoupled theory. So yeah, I don't think it's going to be important. Yeah, I guess you can. Yeah, let me just leave it at that. Thanks.
Do Kramers-Wannier type non-invertible defects always come from X anomalies?
Good question. So the basic answer is no. Yeah.
Mm-hmm.
And well, this is some work in progress, but yeah, basically the answer is no. But in this Z2 case that I'm discussing, the answer is yes. So this is one of the simplifying features of Z2.
Okay, thank you.
Yeah, thank you. Okay, great. All right, so let me just wrap up with the, couple of examples. I went too far, huh? Okay, so here's the examples. So the first example is we can consider starting with SU2, that's not what I wanted to do, erase that. SU2 Yang-Mills at theta is equal to pi. This theory has a Z2 one-form symmetry, which is just the center symmetry of SU2. And it also has a time reversal symmetry, which sends theta to minus theta. And it turns out that these two symmetries have a mixed anomaly of precisely the previous form. So the background gauge field for the time reversal symmetry is the role is played by the first Diffie-Whitney class of the tandem bundle of X in this case. Okay, and so now by the general construction, which I just explained, if I gauge the one-form symmetry, the codimension 1 defect which implemented time reversal should become non-invertible. So in particular, if I gauge the Z2 one-form symmetry, I'll get SO3 Yang-Mills at theta is equal to pi, or really plus or minus pi, because in SO3 theta is 4 pi periodic on spin manifolds. And so the claim is that SO3 Yang-Mills at theta is equal to plus or minus pi has a codimension 1 non-invertible defect n, which comes from the defect for T. Right? In fact, it's only at theta is equal to pi in the SU2 theory that you have both this time reversal symmetry and this anomaly. So in SO3, you expect that you only have this non-invertible defect at plus or minus pi. And so this is somewhat suggestive that maybe there's some phase transition at theta is equal to plus or minus pi. And indeed, exactly such a phase transition is expected on the basis of, well, for example, soft-SUSY breaking arguments. So for example, these authors here argued that the phase diagram of the SO3 theory looks like this in the deep IR. So for half of the values of theta, you're in some totally confining, trivially gapped vacuum. And for the other half of the values of theta, you're partially confining, so you have some residual Z2 TQFT. And the phase transition points are exactly at theta is equal to plus or minus pi. So you can really think of this a lot like in the Ising case, where you have the Ising model and there's a phase transition, and right at the critical temperature, where you have the critical Ising model, there's some emergent non-invertible symmetry in. And so that's exactly this same thing here. All right. Our second example is to consider n is equal to 4 SO3 super Yang-Mills at tau is equal to I. This theory again has a Z2 one-form symmetry, which is the center symmetry. And it now has a Z2 zero-form symmetry, which is generated by the modular S transformation, which takes tau to minus 1 over tau. Now, these two have a mixed anomaly, It's a little subtle to write down an inflow action for this because it's hard to couple to a background gauge field for modular transformations. But I can still detect the anomaly by just doing an S transformation here, and I'll produce some phase, which I now realize in the notation that I've been using should be just B2 cut B2. So it's an anomaly of precisely the previous type. And hence, by the general statements that we've been making thus far, if I gauge the one form symmetry, I'll go ahead and get a non-invertible defect. So in particular, gauging the one form symmetry takes me from n is equal to 4 SO3 to n is equal to 4 SU2 Yang mills at tau is equal to I, technically up to an invertible phase. So for those of you who know, so I should really be talking about SO3 minus here. And so there'll be some invertible phase, but that's a subtlety. So anyway,
sorry, can I ask a question? I'm sorry for just interrupting.
Yeah.
Looking at this anomaly equation, it seems that at the self-dual point, the precision function should vanish unless the anomaly is trivial.
Yes, that's right. So yeah, that's exactly right. So if I fix myself to tau is equal to I, the partition function will be 0.
So what is the interpretation of this?
Well, that's in some sense the interpretation of an anomaly. So this is sort of always the case. How should I say it? So morally speaking, the situation is as follows. Take a partition function coupled to some background gauge field and say that there's some anomaly. Which means that if I do this sort of gauge transformations, I'll get something, e to the I alpha, maybe a function of lambda, and then ZA. You can always consider, though, some global gauge transformations where lambda is basically just set to a constant, say, where that would mean that this is going to be non-vanishing, but this part is effectively still ZA. And so you would conclude that the thing has to actually vanish. So yeah, this is actually a general property. It's related to the fact that if a theory can absorb an invertible phase, then that theory must have some certain anomaly. This is discussed in some papers by Poshin et al. I need to find the exact reference, but I can do that after if you're interested.
Okay, thank you.
Thank you.
Sorry, can I ask, what is the one form symmetry here? The one form Z2 symmetry in the SO3 supernomials?
It's again the, so it's again the, so let's see how to say it best. So in general, you have some spectrum of line defects, of line operators.
Oh, it's the, so you take S-duality and then you have the SU2 and then you say it's the one form symmetry associated to the center of the SU2 after you do S-duality?
I think that's one way to say
that.
Mm-hmm. That's fine also, I guess. Yeah.
Okay. So it's kind of a magnetic one form.
Yeah.
Okay.
If you
I see what it is. Yes, that's fine.
Okay.
Thank you.
In this case, it's sort of, I guess in that language, a dionic one because
yes.
minus,
okay.
but yes.
Yes. Okay. Thank you.
Great. Thanks. Okay. Good. Yeah. So I think that's basically it. So let me just summarize this.
May I ask you a question, please?
Yes, please.
In your previous example of theta equal to pi, does it generalize to SUN for even n?
Yes, it does. And yes, the answer is yes. So in that case, the claim will be that PSUN will have some non-invertible defect. The only catch is that the fusion rules that I gave previously will be slightly different because there we won't be discussing as, sorry. So what you want to do is you want to take this and not discuss the ZN one form symmetry, but rather the Z2 subgroup of it.
Yes.
Yes, then it'll work exactly like I've discussed here. Yeah.
And if I want to do ZN symmetry, it's just a different fusion rule.
Yes.
Okay, but it's still, exactly. There is still, okay, non-invertible.
Exactly. The construction will still basically work, but the fusion rules will be have to be slightly modified because it's now ZN.
Okay, thank you. Sorry, another question related. For odd n, there's no mixed anomaly at theta equal to pi, right?
Right. Yeah.
But there is no smooth counter terms and this kind of thing that was discussed earlier. But this
this global inconsistency.
Yeah, but this doesn't lead to non-invertible defect, right?
I have not really thought about that case, so I don't want to say anything definitive. I'm not sure about the odd case.
Okay, no problem. Thank you. Thank you very much.
Okay, great. Any other questions? Okay, so to summarize the second example, the point was that n is equal to 4 SU2 super Yang-Mills at tau is equal to I, has a non-invertible defect n, and it'll turn out to also have some notion of self-duality because n is Kramers-Wannier-like. All right, so I'm now going to summarize. So are there any questions before I just finish the talk? Okay, so let me summarize. So in the first part of the talk, I told you about the 2D case. So there, the most general notion of symmetry was given by a fusion category. And this fusion category was really the whole shebang. So it contained data both about the group-like symmetries, zero form and higher form. It also knew about the non-invertible symmetries, and it also knew about all of the sort of generalized Hooft anomalies. Now, in higher dimensions, the analogous structure would be that of a higher category. And unfortunately, higher categories are fairly poorly understood. For example, to the best of my knowledge, the full set of pentagon-like identities has not really been written down in a closed form. I think there's some recursive form, but it's not something which is super useful to physicists. I also don't think there's any real notion of unitary structure in a higher category yet. So suffice it to say that the rules of the game here are very murky. But as I warned you at some point, I didn't really bother discussing the full categorical structure at all today. I contented myself with just understanding some interesting fusion rings. And in particular, I gave you a general construction for one class of fusion rings which generalized the Ising category in 2D. And I gave you explicit examples of SO3 Yang-Mills at theta is equal to pi, or plus or minus pi, and n is equal to 4 SU2 super Yang-Mills at tau is equal to I. There are other examples as well, which include n is equal to 1 SO3 super Yang-Mills, Maxwell theory at tau is equal to 2i, SO8 Yang-Mills, so on and so forth. And there are even examples which are not in 4D, but in 3D, say. For example, in some various Chern-Simons matter theories. Okay. So there are various examples, but I think it's fair to say that we're still just scratching the surface on all of these non-invertible defects. And in particular, all of the defects that I discussed today are duality defects. So it would be very interesting to identify non-invertible defects that didn't really have anything to do with duality or triality, etc. Okay, and so I'll leave it at that. Thank you very much.
Yeah, let's thank Justin for the nice talk. Are there other questions?
Ingo, go ahead.
Okay, hi, thank you for the nice talk. Could you go back to the SU2 example with theta equals to pi?
This one.
Right, so the phase diagram. So in the Ising Kramers-Wannier duality example, if you sit at the self-dual point, then another manifestation of this high-low temperature duality, and that it's implemented by this duality defect, is that if you take the energy perturbation and you push it through the duality defect, it reverses sign.
That's
like the energy perturbation is this epsilon field in the Ising model, and if you push it through the duality defect, even though it's not a symmetry defect, but the epsilon sort of, you just get a Z2 action. And is there a similar thing which happens here, that there's something which generates the shift of the theta angle, and if you push it through the defect, it changes sign, something like this?
Yeah, that I'm not sure. Yeah, indeed, for rational CFT, in particular for diagonal RCFTs, it's true that the set of all of the Verdunde lines, and so the set of all of the line defects are in one-to-one correspondence with the set of primaries, and so yeah, I mean the epsilon, let's see, is there, I don't know, that's actually a good question. Yeah, it's not something that we thought about.
Yeah.
I'm not sure. Thank you. Yeah, that's a good question.
Okay, if there are no other questions, then I will stop the recording and we can have a free discussion afterwards.